So this is Mag 9, I guess, the last lecture. And today we're going to be discussing the extension theorem and the geometric interpretation of this theorem. So last week we talked about elimination, and so I gave the analogy with Gaussian elimination and back substitution as a way to anchor ourselves to how to think about these two operations. And extension is like back substitution. And as I said last week, you can't always back substitute like you do in a linear case. So the extension theorem that I'll be talking about here gives us, I guess, sufficient conditions for when this back substitution or extension procedure is possible. And so to extend a solution, we're actually extending from a partial solution to a full solution. And so I'll just I think I'm going to start off with the example from last week, because this will be a running example in today's lecture. So remember last week we had this variety defined by xy minus 1 and xz minus 1. So this is an ideal with two things in it. I'll just call this I. And so let me see. So there was this picture that I drew. I'm just kind of rehashing some stuff from last time now. Right, so this you know what? I'm going to use the different colors. These are the axes. So I'm going to draw in blue what the variety looks like. It's going to be a one-dimensional thing. I guess we haven't talked about dimension, but this is dimension in the pedestrian sense. And this is like VI. And I've drawn it in two dimensions. I guess this is the XZ plane, I hope. Okay. So I guess it's symmetric in Y and Z, so it doesn't matter. Yeah, so this is a picture of the variety. The blue is the variety. And remember, we went and worked out some partial solutions, right? So the partial solutions that we worked out, actually now I remember it was actually Y, not Z. Y. So the partial solutions we worked out, put in green, was this line here. Oh yeah, I actually forgotten we actually have line elements that I can use. I guess next time. Is this the right line? I guess this is. I wanted to say this is y equals x, but I guess this is not the right line. What was it? I guess y equals x was. I've forgotten. Anyway, I'll unmark this. And basically, we've got. I'll repeat this diagram a little bit later on. But basically, we found a line of partial solutions, and we found that over 0, that didn't extend to the full solution. And you can see in this picture, above 0, there's no point of the corresponding variety, no blue point, or no point on the blue line that maps down onto the origin. And we'll see that this is an example of extension failing. In the nonlinear case. We'll revisit this in more detail a little bit later on. But I just wanted to draw this picture up with, I guess, just to get us to think about this with a picture in our heads. So I'm going to state the theorem of extension, the extension theorem. We won't prove this because this requires resultants, and I guess resultants is not in the scope of this course. But what we will do is use I guess use some of the details in this theorem to prove a geometric version of this theorem that we can actually draw pictures and reason with pictures later on. So I'll put the theorem down here. Let's see in the right color. Okay, so the theorem. So this is the extension theorem. So this says the following, and I want to note here that this theorem depends on the generators of the ideal. So let I be the ideal defined by generators. So this is part of the data that goes into the theorem. So this is an ideal inside. I'm going to say complex numbers because we're going to work over complex numbers because a lot of the theorems require our base field to be algebraically closed, and we'll just work over C for today like we did last week. So I'll call this R. And remember, we're going to use the notation R1, R2, and so forth to denote the first, second, and I guess the ith elimination ideal. And so, yep, and I1, right, is equal to I intersects R1. And just remember, R1 is how do I write this? I'll just say it. R1 is the ring where you drop x1. I'll just put in brackets. You drop the variable x1. Okay, and so yeah, so this is just the first elimination ideal. So for each I from 1 to s, you express f in terms of in the following way. So I'm going to put this in a different color. So f I is equal to gi. So these gi's will come back as useful things later on. X1, that's the variable we dropped. So that's got a special place, a special status in I. So you pull out all the powers of you find the maximum degree of x1. You pull that out as a factor, write the gi as the other part of the factor, and you leave the lower order terms. Change color again. You leave the lower order terms as this phi, right? So this is a lower order terms in x1, and I guess, yeah. So I'll write this out a little bit more precisely on the next board. Okay, so where ni is greater than or equal to 0, and gi's is non-zero. These are all in R1, and the degree of x1, I guess I already said this, is less than ni. Okay, so a partial solution I'm looking at this, I'm kind of thinking that this ni had better be positive. Let's erase this. A partial solution A. So remember, partial solutions were points in the variety defined by the first elimination ideal. And this is a point in the space with coordinates x2 to xn. Lifts or extends to a solution.
I think it's possible
that
fi doesn't involve x1 though, right? So in that case, you just want phi to be equal to
true.
fi. Yeah. So maybe just as a special case, if ni is 0, then phi is fi or something like that.
Yeah, let's leave it there. I was worried I copied it wrong out of the book. Yeah, I guess it is possible. Actually, it is possible because when we go to prove the geometric version of this, that does happen. Yeah, so okay, we'll leave it there. So thanks, Dan. So lifts to a solution A tilde if A is inside VG1 GS. Okay, so this right now is a mess of symbols and notations, and it's not clear what the G's mean. We'll have a picture for this when we do the geometric version later on. I guess I don't want to draw the picture now because I haven't introduced any of the things like projections and so forth yet. So I'll just leave this as is, and I'll say that the proof omitted, unfortunately, because yeah, we're not talking about resultants in this course. So basically, I'll talk through this, right? If you want to check if you want to check if a solution extends to the next elimination ideal up, like one up from the one that you're doing now, like we're talking about, I guess this is extending from R1 to the full ring. We can do this for Rj to Rj plus minus 1, right? So you can do this in a stepwise fashion and extend your solutions one component at a time. So that's the first comment I want to make. The second comment is that, yes, I already made this comment. This theorem absolutely depends on f. Changing the presentation of the ideal I, that means changing the generators by choosing a different set of generators, you're going to get different G's. And in fact, you can sometimes choose bad generators such that the G's don't tell you anything, right? So it is possible that these G1s to GS's cut out your entire ideal I1, and so you don't get any information about which solution. No, the F1s to FS's can be whatever you like at this point. I don't think that actually I in the parts of the book I've read, I didn't see anything about Grabner basis that will make this better behaved. It may well does so, but I'm not sure.
I have a question about what's written on the board. There's like 2 ifs in a row. Is it like if and only if?
Oh yeah. Let me just reread. So for each express that where a partial solution. Oh yeah. I guess no. I think I'm going crazy. That's not meant to be there.
Good thing this is the last lecture.
Yeah, somehow just maybe I said something, I went back and I skipped the word, or I repeated the word. Yeah, no. So I think this is a good comment, Dan. That's definitely not an if and only if, because as I said, right, these GIs could change depending on the choice of F, and whether solutions extend, right, shouldn't depend on the presentation, right? But this in the way it's stated here, it does. So definitely is an if, so it's a sufficient condition, not necessary. Okay, so yeah, just if with one F. Okay, so let's any other questions? Okay.
What's the statement
I have questions.
when the x1 degree of phi is 0?
0. Let me see. For each
of
I
f,
express that. Yeah. So if that's 0, I guess in this case, I think in this case, the theorem doesn't apply. And I think in that case, actually, you see that all solutions extend because the equations don't involve x1. So you actually don't need this term to tell you whether things extend. So I guess in that case, the GIs is an empty set. And
I think, wait. I mean, his question wasn't if none of the generators involve x1. It's just, so suppose fi doesn't involve x1, so that, in other words, n1.
Oh, I guess if fi doesn't involve x1, then it doesn't contribute a g, I guess.
Yeah, that's right. Just leave that g out of that set at the end.
Yeah, leave the g out of it. Yeah, but if none of them, sorry, I jumped ahead because there's this condition in the proof, the theorem later on. If none of them involve x1, then yeah, then what I say is true. But if only one of them doesn't involve x1, yeah, then you just forget about that fi. You don't need to use him as a to contribute to a g.
Okay, but is there any true analogous statement to this? Would it be A in V of empty set, or does it just not work?
I think if it's the empty set, it's the whole thing, right? Partial extends solution if A is... Give me one second.
No, I see that there's one GI for every FI, right? Is that correct?
Just take that set to be 0 in that case, and then it'll be true. Yeah.
Actually, Actually, no. I missed something. Is this? It's you have to. It's actually a not in that closed subset. So if you take it to be empty set, it doesn't quite work because then nothing extends. So no. So the point is that if if there are no g's, right, then then this doesn't tell you anything. The theorem just vacuous. It doesn't tell you that things extend. Also doesn't make any claims about extension. So yeah, in that case, the theorem is not so useful. It doesn't. Yeah. Sorry about that. I missed the not in rather than That's
Okay.
the thing we
If
kind of refer.
if only some of the GIs are 0, you just drop those GIs, like from the.
Well, I think we don't think of GIs as being 0, right? Like, how would you get GIs as being 0? Because the GIs are by definition non-zero. That's if you have an xi term there. But if there is no, if let's say f1 doesn't involve any x1s, right, then there's just no g1.
Right. Okay. So it's not that. Yep. I see.
Yeah, so it's not the case that there is actually always a GI associated with every FI. Yeah, so maybe I misspoke earlier when I said, there's a one-to-one. Yeah. Okay, so in the previous example, I guess, right, so I guess I wrote this in the previous, actually, no, this is not the same example. X squared minus y, x squared minus z, right? I1 is equal to y minus z. And in this case, different example, sorry. F1 is equal to x squared minus y. F2 is equal to g. Well, sorry, I skipped ahead of myself. X squared minus z. And so we can put g's here in front of the x's, right? So g1 is just going to be 1, and g2 is just going to be 1, minus y minus z, right? So where g1 and g2 are both 1, right? So in this case, v of g1, g2, I guess is why do I have? I guess it's nothing, right?
Wait. When you write I1 is equal to that.
Because it's 1. And so A. Sorry?
Okay, you write I1 is the ideal generated by y minus z. We proved that earlier?
I think we.
But we could prove it by computing.
I don't know if we.
By computing a Grosvenor basis with respect to the x order, yeah.
Yeah.
So
So we didn't. This is a
exercise.
different example from. Yeah. Where was I? So so this V is empty, and so any partial solution is never in there, I guess, and so every partial solution extends to a full solution over the complex numbers. Now, so every partial solution, and the partial solutions are just parameterized by, I guess, A, right? This is inside A to YZ extends to a full solution. Yeah. So how do we extend it to a full solution over the complex numbers? Well, actually, you just take the square root. All right. Now, because x squared is equal to a, to work out what x is, right? You take a square root of a. Now, you can't do this over the real numbers because you can't always take square roots of numbers, negative numbers. You can't over the real. So this theorem definitely fails over the real numbers. So we need the algebraic closeness of the base field to get the conclusion of the theorem. Okay, so let's move along to the third board. Okay. So now we return to the example of the hyperbola, and in this case, right, f. Right, remember, the ideal I was y x minus 1 and z x. Probably shouldn't write it like this. X y minus 1 and x z minus 1, right? And so we write it in terms of g1x f2 equals g2x minus 1, right? So this tells you that g1 is y, which is, giving names to these factors, right? Then we see that the ideal g1, g2, right? This is just y, z. So this is really just the origin, I guess 0, 0 inside y, z. And so the theorem says that all non-zero partial solutions extend, right? So this is what we found, actually. We worked this out kind of manually last time. We saw that to extend the solution, we have to take reciprocals, right? And of course, you can't take reciprocals of 0. And so, so the theorem, so the extension theorem, actually, extension theorem implies that all non-zero solutions extend, which is what we found. What it doesn't say is that the 0, 0 solution does not extend, right? So it's not an if and only if statement. It just says that everywhere outside of this ideal, in this case, is the origin. Those ones will definitely extend, but at the origin, it might not. And in this case, it does not. Right. So
could we make it
how do we use
extend by getting rid of the minus ones?
Getting rid of the minus ones. Yeah, but you get a different variety then, right?
Yeah. I know that's what I mean. So in a different scenario, would it, in that scenario where you get rid of the minus ones, the solutions of the 0, 0 solution would extend, right? Because you can just pick any x.
Yeah, I guess so, right? Well, let's work it out. If you can pick any. Yeah. Yes, definitely. You just get that line over the 0. Yes.
And so also, if it was like minus, instead of minus 1, it was minus z.
Yeah.
I'm just trying to think of more examples.
Minus z for both, or just for one of them?
I don't know, either, I guess. Probably both of them. It was yeah.
I mean, if you take out both of them, then yeah, I guess so, right? Then xy is equal to z, and x plus 1 times z is equal to 0. So you've got in the second equation, you make that z, right? So you get x equals 1, or z equals 0, and then you gotta fit. Let's work out later.
Okay.
It's always dangerous to make me think while I'm trying to write stuff up. Okay, so I'm gonna move on to talk about geometry of elimination. There's a few examples left in that chapter that I encourage you guys to take a look at. But let's talk about the geometry of elimination, because it really put the theorem that I just presented in picture form, so we can kind of draw pictures and understand what's going on, rather than just stare at variables and equations. So the geometry of elimination or extension, I guess elimination and extension. And again, we'll work over C. We've already said this. So talk about projections because these are important. So there's a map, right, that we're going to use. That's the projection map. I'm just going to define it in a dumb way. Maybe not a dumb way. I'll define it in a way that you probably see in your first class on, I guess, calculus. You'll probably see stuff like this, right? So you want to project onto the L plus first to the last component. So this lines up well with what we've been doing. So if you remember, right, this is like Cx L plus 1 is. This is the Lth elimination ideal, right? Lth elimination ring, I guess. And this is, C. We're just dropping the first L components. And actually, we're not mentioning this in this class. This map, right, defining coordinates in this form is actually a map of F1 varieties, actually corresponds to this inclusion map in some precise categorical way. But we won't mention this in this class, but just kind of putting it out there in case you're curious and you see it later on. So there's a lemma that we should have proved earlier. So the lemma tells you the relationship between the projection of the variety and what we've been looking at so far, which is the variety of the Lth elimination ideal. So this tells us that the projection of the original variety, which means just forgetting about the first Lth components and just looking at what it looks like if you remove those. And if you do this in the algebraic way, like intersect the ideal and look at the zero set of that, there's some relationship. The relationship is that the first is contained in the second. Okay, so the proof goes, you let A be in pi L V, right? So i.e. there exists, yes. Hello? Oh, V is the V of I. Oh, yeah. Thanks. V of I. So maybe I should just write. I will probably drop the I later on. Thanks. So there exists a tilde in V such that the preimage, right? We just take the preimage. So we need to show that if F is in IL, then F vanishes on A, right? So that's how you can show that, it's in the ideal defined by IL. So, so we have FA is equal to, so I'm gonna be slightly naughty here and just depart from the book's notation a little bit. So this thing here, right, is just considering F as an element of the full ring. So F, right, is actually an element of the polynomial ring in the Lth plus first, L plus second to the nth variable. So this pi upper star L is just, it means to consider F as an element of C x1 xn. Or in other words, you want to send F into that ring using the injective, natural injective map that you get from just the subring structure, right? The RL is a subring of this thing, but we haven't talked about subrings and any of that. But so this is just notation, right? Considering f as an element of the full polynomial ring with all the variables there. So what this means is that f, right, or pi star LF is actually in I, right? It's in I because IL, right, if you think of it as a subset of the full polynomial ring, it's part of I, right? And so this is in I. And so therefore pi star LF A tilde is 0 because A tilde is in the vanished, well, it's in the ideal, which is where VI, right? So that's where all of these guys in I vanishes. So this is almost like just a tautology, right? So that's it, right? So what this means is that the projection lands naturally in this variety divided by IL, but IL could be bigger, right? And so that's where, this is kind of where what we're doing with extension, right? We're really interested in V or VI, right? But we're too stupid to get VI directly, so we're going to drop a variable and consider VI1, right? So VI1 has one field variable, it's simpler to understand, right? And suppose we could solve that, right? Which ones of those are actually in the image of pi L, right? So you know, pi L VI is not necessarily all of VIL, right? So that's really what we're doing here. We're trying to figure out what this image is. So in picture form, I mean, you probably, this is the diagram I wanted to draw before, but I couldn't because I didn't have projections. But now that we have these projections, we can draw it. So there's a VI, right? That's what we're interested in. That's a subset of that. There's a this thing, VIL. This is the simpler thing that we think we can understand. This is a subset of this, right? And the theorem that, or the lemma that we've just proved shows us that this actually lands inside VIL, right? This pi L, right? When we restrict the map to pi L, it lands in this thing. And we also have a variety of, well, do we want to say this? Yeah. So we have pi, we have pi L V I, right? And that's actually a subset of this. And we really want to figure out what's going on here. So the partial solutions, oh crap, what have I done? What have I done? So these are the partial solutions, right? So these are the ones that we figure out by solving the equations with one field variable. Over here, these are the partial solutions which extend to full solutions, right? And so that's the one. Those are the ones with the pre-image in VI, and so. Yeah, so that's geometrically, the geometric picture of what we're doing is this, right? So really, you go from the projection and you want to figure out from the projection, how do we go back up? Which points have a pre-image? Okay, so I think that's...
Ken, you've got pi L star F. What is that operation? Is that pre-composition?
Oh, so that's really just the... So remember I mentioned very briefly on the previous board that there's a ring inclusion, right? That map ring inclusion from XL plus 1 to XN into the full ring, that's pi upper star L.
Yeah. What I'm confused about is hang on, so you've got F of pi L becomes pi L star F, right? Not the other way around.
Yeah, I guess that's
like F
kind
pi
of...
L, right? That's what I was
Sorry, say again. Are we like, talking about like here?
Yeah, I mean the order changes between the two expressions.
Yeah, I guess it just does, right? It's just notation, right? It's just right when you pull back a function, you use the map on the spaces to map the point down, and then you apply the function, right? Otherwise, the codomains and domains don't line up.
Okay.
So the content of this equality is simply that if you evaluate a polynomial function on the last L or whatever coordinates of a point, so you have a point, you chop off some initial coordinates, you evaluate the function on the rest, then if that polynomial only involves the variables corresponding to those later coordinates, then it's the same as evaluating the function on the entire tuple. So that's the right-hand side of this formula says, if you have a polynomial function that only depends on x3, x4 up to xn, it doesn't matter whether you evaluate that on just x4 up to xn, or you pretend it's a polynomial in more variables and evaluate it on a bigger tuple. So that's the content.
And then the pi L star sends you back down to the smaller space.
So pi L star just means think of your polynomial in x4 up to xn as a polynomial in x1 up to xn. That's all.
Yep. And it operates on f to do that.
That's right. Yeah. I guess on the left hand side, f is a function, and on the right hand side, it's a polynomial. It's an element of the polynomial ring. So then pi L star is a function that takes a polynomial and outputs a polynomial. Yeah.
Sure. Yep.
Cool. Let's go to the board on the right. So now I can. Oh, it's not moving yet. Did I move too far? Okay, nope, I think that looks good. So now I can draw that picture that I wanted to draw at the beginning, and I guess what colors did I use? I used blue. So the picture from the beginning was really this is just copied from the book. I'm just adding some colors. So this is the parabola example. And I'm drawing some blue lines and white lines to indicate which are the partial solutions and which are the axes, right? So blue will indicate the variety. And we have these maps, right? Okay, so this is pi L. Pi 1, I guess. Well, just pi 1. And you have these are the full solutions. These are the partial solutions. And there's this plane that we're looking at here. There's like the parabola and the partial solutions all live on this YZ plane. So this is a YZ plane. Is that right? Yeah. So this is the YZ plane. And yeah, so the partial solutions here, right, is V. Yeah, I'll just yeah, I think it's fine. Yeah, so this is kind of what the picture looks like in the hyperbola example. I think, yeah, so we have this point in the middle, right, that's missing. And so pi 1v is actually this line minus the origin, right? So it's actually not an affine variety, right? An affine variety has to have equations, right? But you're missing it's got the equation defining this line, but it's missing a point, right? So so that's not affine. And so so in general, we want to figure out how we want to figure out what is missing, right? So we've talked about these G's, right? These are the things that that may be missing from the solutions that extend, but we want to know how big it is, right? Because we've kind of already talked about this possibly failing. So let me write up the geometric version of the extension theorem, and this is really just a restatement of what we've gotten before, but we're going to use projections to explain everything, and also we're going to restrict it to just extending up one variable. So this is a geometric extension theorem. So F1, so again, we're going to define I with respect to some generators. V is the ideal defined by I, and I1 is first elimination ideal, right? And we're going to do the same thing as before. So I'll kind of brush through this quickly, define the GIs as we did in the earlier theorem, as in extension theorem, right? Then we have this decomposition. Vi1 is equal to pi 1v union some big thing, v g1 gs intersection v I1. Okay, so yes, so where pi 1 is projection on the last n plus 1, n plus first components. Projection onto last n plus 1 components. Basically, we dropped x1, so that's it. So I want to make a comment here about the book. The book has a few typos in this section. They keep confusing I with L, right? Because we talk about the Lth elimination ideal and maybe also the 1 and L. We talk about often the first elimination ideal and the Lth elimination ideal, and I guess they look kind of similar, right? But so they sometimes use I and L interchangeably. Not a big deal, but just beware if you're reading. So this decomposition is not always useful because so this theorem basically follows from before, right? But it can happen. It can happen that V.
Sorry, did you say they confuse I and L or 1 and L?
Sorry, 1 and L. So we often talk about the Lth elimination ideal in the general case, and then there are many places where we only go up one step, or we only talk about dropping the first variable. So that's 1. So sometimes L is meant to be 1, and yeah. Guess it's easy to make this mistake. So sometimes this variety cut up by G1 to GS is actually all of Vi1 and tells you nothing, right? So in this case, the extension theorem is not useful for telling us anything. So an example where this happens is, again, in the previous example, I'm going to add some junk to the generators. Again, this is a hyperbola example. I'm going to add this junk to the generators, and in fact, we can show that that's really not like the stuff that you add doesn't change the ideal, right? They generate the same ideal. But now if we carry out the procedure of defining these Fi's and Gi's, we're going to have y minus z. All right, you can already see that junk is going to get in the way. And it's going to mess up our conclusions. So let me just move along here. Right, so here's an exercise to show that those two generate the same ideals. You can probably even just eyeball it, but they do generate the same ideal. Right, now if you want to define these GIs, right, you can already see what the G1s and G2s are supposed to be, but G1 and G2, right, they're the coefficients of the largest power of x, which is x squared in both cases, and so they're both y minus z, right? So this generates I1. I1 was y minus z, right? So this doesn't tell us anything, right? This bad locus, right, where we don't know where the things extend, has taken up the entire thing. But we know that solutions extend, right? We had better generators before, and we were able to get a conclusion. So what this says is that if you have generators that were chosen kind of badly, right, or given to you not in the way that you want, you're going to end up with this situation. So this can happen, right? So the next theorem is the The next theorem is really the cure for this. I don't know if I'll get to the proof of this. I'll definitely have time to sketch the proof, but the statement is kind of interesting. So this is called a closure theorem. And in fact, we can't prove the first part, but I'll tell you what the first part is before making any comments. So we'll keep notation. Maybe I should have just done this earlier. So the first statement is that VIL, so we're back to L now, not 1. So this is just a general statement of the Lth elimination ideal, is the smallest affine variety containing pi 1v L, see I messed it up too, inside Cn minus L. Right, so in other words, well, this is really what is called the Zariski closure, but I don't think we've talked about any of that here, so this is just a name for us to kind of look forward to in the future. But you can think of this as like the smallest affine variety, meaning like smallest with respect to inclusion. So if you look at all the affine varieties contained, the smallest one is pi L v. So 2. So when v is not the empty set,
you mean the smallest one is VIL?
There is an affine variety. Say again?
You said the smallest one is pi LV, but you meant the smallest one is VIL.
Oh, yeah, I did. Sorry. I already forgot what I said. Thanks, Dan. Yes. Man, I swear, if I uploaded as many YouTube videos as you do, it'll be like a comedy of errors.
I have the benefit of being able to edit
so
out
there's an
my
affine
errors.
variety W, right, inside VIL, such that when you get rid of it, get rid of it, right, then this is inside V, man, pi LV. So just to contrast what we said before, we said pi LV is inside VIL. He was saying if we take away an affine variety away from VIL, then that's going to be inside pi LV, right? So somehow we take a small piece away, then we end up being inside pi LV. So these two varieties are kind of close-ish to each other in some sense, right? So the proof 1 requires no Stalin sets, so we can't prove it because we haven't done it yet. So proof omitted. Part 2 we can do, but yeah, I guess I'll do it, right? I did say I was going to give you half an hour to say some stuff, Dan. How much time do you need? Do you want me to do it, or are you like gearing to say some stuff?
No, I mean, it's not important really what I have to say, and it won't take up a whole 30 minutes anyway. So.
Okay, fair enough. So I'm going to chuck through this proof because this proof is fun. It's a little bit complicated, but we'll see. So we're going to prove this for L equals 1 only. The book says that there is a proof for general L coming later on, but I guess for us, we're just going to do L equals 1. And this is the last big theorem we're going to have in this class. We're coming up to the last part. So did I not move over for this board? Sorry.
No, it was
now
fun.
I moved over.
No,
okay.
it was fun.
I guess now we can. Oh, okay. All right, cool. Okay, so the proof. So the proof actually is, the proof requires a little bit of changing the generators around. It's kind of interesting because we saw that in the previous example that there were some bad generators that caused us to not be able to invoke the power of this theorem to make any conclusions. the proof actually undoes it, all right, and we can get better generators. So so from the geometric extension theorem, right, we have a decomposition like this. This is just kind of rewriting what I had in the previous board, but let's do this. I like made the same mistakes as I'm writing it down. That's kind of crazy. There we go. So now all the L's are 1s, I guess. So we're gonna call this thing W. And W as in like the statement of the theorem says that you take a piece W from VI1, right? You get rid of it, and that should be contained in pi 1V, right? But it can happen, as we saw in the previous example, that W is all of VI1, and then, you know, the statement of the theorem is kind of vacuous. So of course, when you take the whole thing away, yeah, the empty set is inside there, right? So, but we wanted, hang on, did I say W not equal? Yeah, anyway. So yeah, so we obviously don't want W to be the all of VI1 because that's stupid. So so 2 follows if W is not VI1, right? So the rest of this proof is to deal with the case where it is VI1, and we're going to shrink it. So the rest of proof, right, we need to shrink W if W equals VI1. Okay. So these kinds of arguments are kind of commonplace in algebraic geometry, right? You have, you know, some variety, you need to make it smaller, so you do some stuff to it, with nitty-gritty stuff, and then I mean, here we're doing something kind of relatively simple. We're just kind of changing the generators around. We're not kind of, yeah, none of this is crazy. So, but these kinds of arguments you see again and again. Okay, so we're going to assume that this is the bad situation where W is VI1. Then the claim is that VI, right, is equal to V of F1 to Fs, G1 to GS. Okay, so what is this saying? Remember, VI was just V of F1 to Fs. So what this is saying is that adding these extra G1s to GSs don't change the variety, right? It's the same variety. And so what we have to show, you know, proof of claim, all right, what we have to show that if A is inside VI, right, then I'm going to use the same notation as before, pi 1 star G, GIs all vanish at A, right? So you take a point that's in the original variety and you show that these GIs, right, they all vanish at A. So adding them to the set of generators don't change anything. All right. So the hypothesis that W is equal to VI1, right? W equals VI1 implies that the GIs vanish on pi 1a. All right, it's just, yeah, that's just saying that the GIs, yeah, they all vanish on pi 1a, i.e. Pi 1 star G I.
Ken, can you hear me?
A equals 0. Yep.
That's an I sub I?
Yep.
I sub 1, right? Or L?
Ooh, where's I sub 1? Yes. No such thing as I sub I's.
and I don't really understand. You say pi 1 star of GI, but the GIs, they could involve X1, no? Oh, no.
No,
you
you
factor out. Yeah, of course. Yep.
Yeah. All the x1s are gone, right? So the GIs are definitely in the I guess we don't call it the elimination ring, but it's in, yeah, x1's gone. Yeah. Okay, so it vanishes on A, right? So that's good, right? I think that's basically what we need to do, right? And basically the hypothesis forces them to vanish on pi 1A. So yeah, so really I should have called these GIs pi 1 star GIs, but you know what I mean. Okay, so let's move on to the next board. Okay, so why are we doing this? Why are we chucking in these extra generators? We're going to use them, right? So we're going to use these extra generators to knock off the bad things in FIs, right? So now let I tilde be this thing of all of these FIs and GIs that we've gotten so far. And remember, changing this ideal doesn't change the variety, right? And so so by 1, V of I1 is equal to V of I tilde 1, right? And so why is that? What is 1? Firstly, 1 is basically telling us that the I and I tilde, right, I'll write out the argument. So why is that, right? So since V of I, right, is equal to V of I tilde, which is what we just shown, that the same ideal, right? So the projections under the pi 1 map is the same, right? This is the same as the pi 1 of
Did I
V
miss what 1
tilde.
was?
Sorry?
Did I miss what 1 was supposed to be? Didn't see
Oh,
it.
1 is just the x. Are you talking the subscript 1 in the ideal?
No, you've got by 1. What is
Yeah,
1?
that's the first part we didn't prove.
Oh, 1 is the.
Oh, the theorem.
Sorry, yeah. Sorry, yeah. I was just gonna get to it because I need to use it right about now, right? So remember the first part was saying that VI1 is the smallest variety containing pi 1 of V, right? And so they're equal. So I'll write it out here. So this is the smallest variety containing pi 1 Vi, and this is the smallest variety containing pi 1 V. That's part 1. That the green is a statement of, is a claim of part 1. And so since these are equal, the original, right, those are equal as well. So this uses part 1, right? So we haven't changed, not only did we not change the original variety, the first eliminate, well, the VI1 and VI tilde 1 are also the same. So that's nice, right? Because now we can play around with the generators and try and do some stuff, right? So this is the key trick. This is the key trick in the proof, right? To attempt to, I'm going to say attempt to because it doesn't always work. Shrink W, what we do is we define Fi tilde to be Fi minus Gi x1 and I. So where Gi x1 and I are from the previous theorem, or actually, yeah, the extension theorem. And we just knock off this term. And so this generates the same ideal, right? And I guess then I tilde equals to F1 tilde, Fs tilde, G1, Gs is equal to I. Well, it's actually equal to, wait, hang on a second. Why do I have I tilde? Oh, no. That's because hang on. The claim is that this I tilde is generated also by F1 tilde, F2 tilde, Fs tilde, and G1 to Gs, right? And I tilde is defined as F1 to Fs and G1 to Gs, right? So why do these generate the same idea? Well, because G is in it, you can actually just, we just done some linear thing, right? And so these two ideals are actually like this ideal here, and this ideal here, right? Ostensibly given by different generators, but really they're the same ideal, right? Okay. Okay, so now that we can, I don't have to move. So now that we've got this, right, we're going to apply the geometric extension theorem to vi tilde. So now this is this bit is actually maybe this is another interesting thing that they did. So apply the geometric extension theorem. So remember, the geometric extension theorem depends on the generators, right? On vi tilde, right, equals v of, I guess now, right, I should actually write out what the generators are because I'm applying it to the f tildes, not the f's, right? We'll just get the same result, right? So now we've changed the generators, we apply the geometric extension theorem, which means going through the whole thing of defining new GIs, right, from these generators, and we're going to get different decomposition, right? And we may, I should say, we may get a different, decomposition. Vi1 equals tilde pi 1 v union of w tilde. So w tilde is whatever, the new g, we're going to get some new g1s to g, maybe 2s in this case, and we're going to get a new w tilde. And we're going to keep doing this, right? Each time we do this, we can just repeat the procedure, and we're going to keep doing this until w tilde gets small, right? Until it's not all of vi1, right? So we're going to keep doing this until w tilde shrinks. All right, then we're done, because once it's small enough, then we can just use that as a statement of the theorem, and then that's it, right? This decomposition assures us that vi1 minus whatever w tilde 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 gets produced at the end, it's going to be contained in pi 1 v. Okay, so the only thing we have to kind of worry about here is that what if w doesn't shrink, right? What if we keep doing this and w remains vi1 forever, right? So we have to just knock this last case out, and then we're good. So if w doesn't shrink ever, right, i.e. the above procedure continues indefinitely, right, with w equals to vi1, right? So in each iteration, the x1 degree of the fi strictly decrease. So in each iteration, the x1 degree of the fi's strictly decrease. All remain at 0. Okay, because what are we doing? We're taking the biggest power of x1 and just getting rid of it. So eventually they're all going to be gone, right? So what this means is that if we get to the point of this continuing forever, that means the original polynomials were really in R1, right? So this means V can be cut out by polynomials in Cx2 xn, right? So you know, the original, so V, there can be a set of equations or F1s or FSs that cut out V that don't involve X1 at all, right? And so what this means in this case, I guess I'll put it kind of here, so at the end, right? So i.e., right, every solution, partial solution, extend, and pi1v is actually equal to vi1, and so w equals empty set works, right? So the last little bit is basically saying that, yeah, if we're not able to shrink w, well, w was the empty set anyway, and so we can just say it's the empty set and then part every solution extend, because the variety is really living in x2 to xn, right? And so that's it. So that's the geometric version of the extension theorem in one variable. And I think to finish off, I want to just revisit our first example and see that the extra crap that we added to the generator is actually, gets eliminated by this procedure. And I guess, you can probably all see that already, but let me just write it down as the last thing to close out the example that's been running through this class. So the last example, going back to f1 equals y minus z x1. Remember, sorry, x2, x squared. Remember, we added this stuff to the hyperbola, the very nice equations that we had, and that messed up our application of the extension theorem. Right, so this is xy minus 1, xz minus 1, right? So the procedure in the above proof, right, what it does is it takes the g, actually subtracts away this term and this term, right? So the procedure in the above proof gives f1 tilde to be xy minus 1 and f2 tilde to be xz minus 1, right? Yeah, so it essentially just does f1 tilde. I mean, I can probably just write this out, right? This is actually f1 minus g1, right? x1 squared, and this is f2 minus g2 x1. There's no x1. Let me erase that. Yeah, so where g1 and g2, right, are just y minus z, right? So we've seen this before, and yeah, it's just the procedure in the proof just eliminates this, and it keeps doing this until the w is small, right, or small enough, so that we can stop. Now it still doesn't tell us everything. It doesn't tell us exactly what the pi1 of v is, right? Because in fact it won't, because sometimes it's not affine. No, actually it won't, right? So but then at least we have some handle on shrinking this so that we can say where there's like a non-empty set where things can extend. So I think I'll stop there, and yeah, I got like 15 minutes or so for Dan to say some stuff to wrap up the course.
Yeah, thanks, Ken. Maybe I'll make a comment on the proof as a starting point for these final comments. So as we introduced it, algebraic geometry is the study of systems of polynomial equations, and yeah, we maybe sometimes care about actually solving them. I guess it's interesting that, as an algebraic geometer, very little of my time has been spent actually attempting to solve equations in any real sense. I suppose it's maybe more accurate. I mean, obviously, what does it mean to solve a system of equations? Maybe there's one solution or a finite number, and then you mean write them down. But if you can't write down the solutions in any meaningful way, what does it mean to solve a system of equations? well, what do you even really mean when you actually get a number as a solution? I mean, suppose you have x squared equals 2, and then you write down the solution is, well, x equals plus or minus root 2. But what's root 2? It's just the unique positive number whose square is 2. You didn't do a damn thing, really, right? Writing that down. It's almost tautological.
Yeah.
So what did you solve that equation? Well, it's not so obvious what solving something means. It only has a meaning if you already have in mind some more primitive, explicit way of expressing the thing. So in the case of x squared equals 2 and x equals root 2, there's not really much of a difference between the first and the second, and that's because the root 2 is in some sense no simpler than the equation itself. Okay, so when you're trying to solve something, I guess what you probably mean is taking something complex or which is implicit and converting it to something which is more explicit, which you didn't already have sort of sitting there staring you in the face in the original system of equations. And that's a theme that's run through this entire course, right? So we discussed at the very beginning, I think it was pre-course 2 or 1, I talked about when you're solving systems of equations, you do algebra. And what's algebra? Well, algebra is taking one system of equations, perhaps a single equation often, and transforming it into an equivalent system of equations. Equivalent in the sense that they have the same solutions, but we know very well that you can have two systems of equations with the same solutions, so they're equivalent in that sense, but they may be very different in the sense that one of them makes the set of solutions more explicit in some way, or easier to apprehend, or easier to work with. And perhaps the overarching kind of point of the course has been that among systems of equations, there is a clear favorite. There is something like the good system of equations, and that's a Grosvenor basis. Right? So, given any ideal, or given any variety, there are many systems of equations which will cut it out, and among those the Grosvenor bases are quite special, and reduced Grosvenor bases are even unique. And this object, this reduced Grosvenor basis, is something you may have never seen before, and I think it's learning that this thing exists and what it's useful for is kind of the main thing I want you to remember from this course, that this object, that there is such a thing as kind of the good system of equations, which is easy to solve, in quotation marks. And that's kind of the content of the elimination theorem and the closure theorem and so on, is to say in what sense precisely a Grosvenor basis is an easy to solve system of equations. And regarding the proof that you just saw,
which theorems from today?
Yep.
Which theorems from today involved Grosvenor bases? Because I don't remember them being mentioned.
Oh, it doesn't, I don't think. Right?
Because you were just saying that the Grosvenor bases are like important because they apply to the extension theorem, right? What did I miss here?
yeah, I guess it's more in the proof than in the statement. So yeah, this is a hard question to answer.
Right.
But if you look at the proof, I mean, it's how are you actually going to prove these statements? Well, you're first going to compute a Grosvenor basis of the original ideal, right?
Right. Okay.
Yeah, so perhaps it's more.
Where did we do that?
Well, we didn't give proofs.
So, all of the I
Sure, yeah.
elimination stuff, they depend on having Grosvenor bases to be able to determine what they are, right? Like you can define them abstractly, but without Grosvenor bases with the Lex order, how are you going to find the generators?
Yep.
That's right.
Right? I think that's where it comes in,
makes
right?
sense.
Yeah.
Yeah, it's a good question, though. Okay. The other thing I wanted to remark on.
Did you have
was,
more to say, or can I fire more questions?
Yeah, let me just make one more comment about this proof before
Go
I
ahead.
forget it, because I hadn't prepared to say it. I think maybe it didn't quite follow all the details of that last theorem, but I think it's an excellent place to stop, because this illustrates what algebraic geometry is actually like, right? So this mixture. So we started with a picture. We're trying to reason about a geometric thing, right? You take an algebraic variety, say some surface in three-dimensional space, you're projecting it onto some plane, say, right? Maybe you're looking at its shadow in one of the coordinate planes. You project it onto the plane and you want to know what is that projection. That's a very geometric question, obviously. But once we start into the proof, very quickly we're doing some sort of complicated algebra with ideals, with Grosvenor bases, with generators. We're pulling out coefficients. And in some sense you could ask, well, where is the geometry? Well, it's still there. That's what geometry is, right? So this mixture of the doing the geometry and having the pictures in your head that are geometrical, and at the same time you're learning how to recognize that in these algebraic manipulations is very much what algebraic geometry feels like. So this proof is kind of a better illustration of what algebraic geometry is like than maybe some of the earlier things which have a purely algebraic flavor to them. Yeah, so that's where I wanted to finish these broad comments. You had questions, Billy?
I was just thinking about the sort of the root plus or minus root 2 comment you made. So it seems like you were hinting at some equations being more explicit than others, and I was just thinking about the square root of 2 thing. That seems like we have notation for expressing like the solution just in terms of numbers and not equations, when it's the solution to a polynomial in one variable. That's like when it's one variable we can express things like root 2 and root 3 and whatnot, but we don't have an analogous thing for like multiple variables or so I guess you're saying like Grosvenor bases are perhaps the most explicit form. So I guess like I don't know, a Grosvenor base is just like a generalization of the idea of like the notation square root of 2 or something.
That's an interesting idea. I don't know how to really make a formal statement to the effect that Grosvenor bases are like the most explicit form. It's obviously true, because you can kind of give many examples which illustrate that. Actually, I had one prepared that I'll maybe give as a bonus talk at some point. You can formulate finding colorings of a graph in terms of finding a Grosvenor basis, and then you can see very clearly there, and in many other examples like that have a combinatorial flavor, that you start by expressing a constraint, and the constraint are the generators of the original ideal. And then, like a bit like the axioms in a first-order theory. And then computing a Grosvenor basis from that original set of constraints is kind of like working out all the consequences of those original constraints until you've got to a form which kind of exhibits the totality of all the implications in some sense. And that's what a Grosvenor basis is like in these combinatorial examples, when you encode combinatorial constraint problems as kind of geometric problems. So yeah, I don't know how to technically say what that end result is, apart from saying it's a Grosvenor basis and these theorems that we've talked about and those examples. But yeah, that's the vein I'm kind of thinking in. Yeah.
Okay, so when you were saying some equations are more explicit in some sense, like you said that phrase a couple times, are you claiming that that reduced Grosvenor bases are the most explicit, or is there a setting in which like maybe they're not the most explicit and some other form is more explicit in some sense?
Yeah, I don't think I have a good answer to that question. I'm not aware of.
So Dan, isn't presenting?
Sorry.
Can you hear me?
Yep.
I was gonna say, isn't presenting the solutions of x squared equals 2 as the points, right? Isn't that just like the parametric form, just with no parameters, right? So if you have a set of equations that were like kind of, you can rationally parameterize them, I would argue that the rational parameterization is the more explicit way of looking at the variety, right? That's kind of solving it, right? In going from implicit equations to a parameterized form.
Yeah, that's a good point. I would read it differently, though. I would read it as saying that maybe Billy's question just doesn't have a clear answer because it depends what you mean by explicit.
Okay.
Yeah, right. So let's take an example where we have a parameterization.
Well, my question was what I was asking you what you define as more explicit, but okay.
Dodge the question.
Yeah, I'm saying maybe you have expressing confusion as to whether I believe in a single answer, I guess. So, yeah, if you have a parameterization,
okay, right.
one way of, I mean, you may have two very explicit ways of presenting the variety. One is a parameterization and one is like a Grosvenor basis. And which is better? Well, for different purposes, one or the other is better. So in some sense, maybe neither can really lay claim to being the one true explicit form. Yeah.
Well, with the parameterization, aren't you using things like the square root of 2, which we were just sort of discussing, is kind of like just a cheating version of stating in the equation?
Yeah. It depends what's in the parameterization, I guess. Yeah, it's I think it's difficult to really discuss this without examples, so it's an interesting line of thought, but I don't know that I can say any more than I have already on it.
I mean, in mathematics,
Okay.
you often want to have all the different ways of representing an object, right? And no one of them is always better than another at all times, right? It's useful to have all of them at your fingertips.
Yeah, that makes sense. Yeah, thanks, Billy. Other questions?
I mean, well, I guess what I'd like to see from here, if you can suggest any good ways to go forward, is like we have this cool machinery, and it's like, what problems can I solve now, other than sort of hand waves? You can do stuff with variety. Do you know what I mean? It's nice to be able to say, I can solve this class of problem now.
Yeah. It depends which part you're referring to, but if
it's lovely and fascinating. Yeah, it's
so
lovely and fascinating. It's sort of like it's leaving me wanting to know a little bit more, which I guess is the idea. But yeah.
Yeah, the next, I think the book's actually quite good. So then after this, it proceeds to talk about how you would find a set of generators for. So if you want to do operations with these varieties, like you want to take their union, you want to take their intersection, you want to cut one variety out of another, so take the complement, using these Grosvenor basis methods. So you can just deploy all the stuff we've learned to write down generating sets for all of those. And in terms of what you would do with that, well, it means that any time you can write down your problem as a set of polynomial constraints, you can reduce essentially the problem of understanding your system to the problem of computing a Grosvenor basis. That may not be easy, but it means that you've got this reduction of an enormous range of problems to this one algebraic process, which has been very heavily optimized and for which you can find widely available very good implementations. Graph coloring is one. So That's a very easy problem to encode as a system of polynomial constraints. It's not meant to be obvious how you would do that, but it's not difficult. Yeah, I'll explain that at some point. But many combinatorial problems can be encoded that way. It's not always the best way to solve them, but that's kind of one.
I mean, I confess that combinatorial problems don't especially fascinate me. But yeah, okay. So what you say? I mean, I see what you're saying more generally, though. It makes perfect sense.
You've got
where do the field coefficients show up when you're encoding a constraint problem, like a combinatorial thing?
Yeah, it's quite interesting. So
like,
when
are you working over complex numbers or something?
Yeah, so you could do it in different ways, I guess, but the typical way of encoding a graph coloring problem as a sort of Grosvenor basis problem is to have the colors be roots of unity. So if you have 3 colors, you take the third roots of unity, and those are your colors. And then the fact that adjacent vertices rather, have different colors, that constraint can then be encoded as a polynomial, like the vanishing of a particular polynomial, in a way that's maybe not completely obvious, but I could explain in 2 minutes how it works. I feel like at this point maybe I should have done it. But yeah, so that's how that works. You use roots of unity, and that's a kind of common trick for encoding finite combinatorial problems, is to use roots of unity in there. It's of course just a sneaky way of putting cyclic groups into your picture, right?
Is there a sense in which you make use of the rest of the space, because there's a sort of continuous amount of stuff left, and you're sort of encoding your problem by making use of these discrete roots of unity?
Yeah, you could have just embedded. You could have just taken a field extension of R with the roots of unity and probably essentially got the same effect. Yeah. Let's take some more questions, but follow me, please. So we're in the right spot for the next part. Please detach from the orb.
Much down in Canada, everyone. It's been great. It's been a pleasure. See you guys next time, whenever that is.
Yeah, thanks everyone. This has been really a blast, and thanks for showing up, and thanks for your questions. And let me explain what the final challenge of this course is. There's a waterfall if you follow this path. Can you see this path here? So if you follow this path to the end, to the island, there's a waterfall, and the exam is only one person will pass this class, and it's the person who gets there first. Nobody got here with their car?
No. I had to ditch and run the rest of the way once I got to the bridge.
I can see a bunch of them on the bottom of the lake.
They're all in the water.